Hello and welcome to the Oceanology International Connect session on unmanned vehicle operations. So my name is Richard Mills. I work for Kongsberg Maritime in marine robotics, and I'm going to be chairing the session this afternoon. We've got 4 speakers to talk about how they use vehicles and very different types of vehicles in some different applications as well. So first of all, we've got Trevor Pugh from UTech Survey based up in Aberdeen, and he'll be speaking to you about using Gavia vehicles. He's going to be followed by Keith Wallace from Blue Ocean Monitoring, who's calling in from Perth in Western Australia, and he's going to be talking about using IVA vehicles in very low logistics operations. He'll be followed by Chris Eccles from Oceaneering based in Houston, and he's going to talk to us about using the Freedom vehicle and some new innovations they've had. And finally, Adam Mara from Bluefin from General Dynamics Mission Systems is going to talk to us about using the Bluefin 9 in some very challenging, very shallow water operations. And Adam's calling in from Boston, Massachusetts. So we're going to start with Trevor. So Trevor works for UTech Survey. He's the technical authority on survey for them. And he got a degree in geology and geophysics from Imperial College. And he's worked in offshore survey since the early 80s. So we're all the new boys for you, Trevor, I'm afraid. His experience ranges from very shallow water geophysical, geotechnical surveys to management of ROV vessels, and specializes in out-of-straightness surveys and spool piece metrology. I'm not even going to pretend to understand what that one means. Recent work at UTech Survey is focused on the Gavia AUVs and the development of automation and implementation of remote services. So he's based in Aberdeen, and he also leads UTech's knowledge transfer amongst personnel based in their Houston, Perth, and Abu Dhabi and Singapore offices. So, Trevor, over to you, please.
Thank you. Right, so I'll just share my screen and then we can get on with the presentation. So you should be able to see that. And we're going to talk about field resident Gavia AUV for wind farm inspections.
That's not come up yet, Trevor.
Yeah, so we're going to, so thank you. So we're going to talk about field resident Gavias being used for wind farm inspection. So to just cover the things that we're going to be talking about, we're aiming to replace pole-mounted multi-beam being done from a crew transfer vessel or other similar small vessel with an AUV, which is carrying multi-beam and side scan. And the big advantage is it can gather data at the optimum height above the seabed rather than a multi-beam on a pole, which is just at the water depth that you've got. We can also, by putting the vehicle and the sensors below all the wave action, we can get better quality data in a wider range of weather conditions. Now, the big bonus of this is we don't need a dedicated vessel. Right? We can launch from anything, the CTV, and the Gavia can go off, do its survey, and then rendezvous with the CTV when it's finished. So that lets the CTV get on with its own work. So we remove a survey vessel from the field. And then we can also reduce the head count that are operating the AUV by remote mission planning and also remote data processing. But we still do need an operator in the field. So to explain more about the Gavia, it's a 3.5 meter long, 200 mil diameter torpedo, essentially. Propeller at the back, and then the sensors mounted in a series of modules that click together very easily, battery powered. Got a control module which houses a lot of the INS and navigation software. You reference the INS by using GPS that's built into it, so you can feed that RTK or corrected positions. That seeds the INS so that when it goes subsea, it's navigating on INS DVL. Right, it's, as I say, we can easily move it to a job and move it from boat to boat because it just breaks down into modules about 300 mil long. Typical survey speed is 3.5 knots, and obviously depth range 1 to 1,000 meters. Doesn't really apply in wind farms where we're working in more like 20 to 60 meters. We typically get 6 hours on a battery charge, and you can change out the battery modules if you want to keep the same vehicle running. 120 kilos, so 2 men can lift it and move it around the deck, carry it onto a boat. Looking at some of the sensors, then we don't have a Reson or R2 Sonic multi-beam. We have the Geosloth Plus, which is a 500 kilohertz interferometric swathe bathymetry system. Now that is probably our most difficult part in getting gavias adopted by the wind farm operators. Their specifications are written for pole-mounted multi-beam. And we spend a lot of time explaining to them that interferometric is as good, if not better, in certain aspects than multi-beam, but it doesn't meet the specification that they've got written. So we have to try and persuade them to accept this alternate system. It's very efficient at what it does. That's the whole point of interferometric. You can get a greater range of swathe in a single pass. We typically work at a 5 meter altitude, and that will give us 40 to 50 meter swathe of good quality data. There's been various papers that say that it's IHO special order compliant, but as I say, that's our challenge, is to persuade the wind farm operators of this. We can also use, there's a backscatter option within the system, so that gives you that pseudo side scan sonar, which can then complement the Marine Sonic dual frequency side scan that we've actually got fitted. To match with the swathe width, then we normally work at the 900 kilohertz side scan. The sub-bottom profiler, not the strongest sensor on the vehicle, just by the size limitations and power limitations, but it's good for export cables, but it would struggle with most intra-array cables, but it is there, and we can program the Gavia to fly in this sort of mission where it goes backwards and forwards across the cable to get a series of depth profiles. The camera is a monochrome camera. It wasn't as widely used as it should be when we've been doing pipeline inspection in deeper waters and route surveys. It has come into its own in the shallower water of the wind farms. That's because we're getting quite a lot of ambient light coming down to the seabed, and that helps, that gives us better lighting than we get from the built-in lights on the Gavia. So we're able to get good quality images with a wider coverage than we used to get when we're just reliant on the Gavia camera. So the image in the top left is where we've mosaiced some images of a cable coming in, going over anti-scour rock dump. And we mosaic those images together to form a point cloud, which you can now sort of scale from and take measurements from. Now we can also just mosaic by the Gavia position, so you can just stitch the photographs together using the metadata that's associated with each image. Right? And then once we've got that georeferenced point cloud from the mosaicing, that can be imported into the multi-beam side scan data. Obviously you need good viz. If you can't see anything due to mud in the water, you're not going to get much, but we're finding that a lot of the wind farms actually have good viz. Then a recent, a couple of years ago now, we invested in a BlueView module. Right, that gives us this 2.25 megahertz imaging sonar, which can produce a point cloud. Now we can use that for detailed scour surveys, but it also fills in the what's known as the nadir gap on the geoswath. Unlike a multi-beam, where you can have beams across the full swathe, the way that the interferometric works is actually a gap in the data below the Gavia. So we can, by using the BlueView as a gap filler, then it means we can increase the line spacing. We don't need to get the overlap that we used to do. There is another module, it's called a scientific module, and that is basically an interface for any other sensor that you want to attach to the vehicle, either internally or externally. So Teledyne, the manufacturer, have developed a couple of magnetometer options, towed and built in, that can go with a Gavia. And then, of course, you can add video cameras or even the a laser profiler, all within the weight limits of the vehicle. Right, it's not a Hugin with a huge payload. It's a 120 kilo torpedo. This is the launch and the recovery aspects of it. Because of the vehicle size and portability, then we can go on to almost any vessel platform. We prefer to use some form of crane to get it into the water. Gone are the days of manual handling, 120 kilos in and out of the water. So vessel crane, we can launch, recover with soft strops, boat up for recovery, or we've got a variety of cages which let you deploy from bigger vessels with higher freeboard, and you just fly it in and out of the cage. You can put it in the water at a quayside or a beach, and it can then travel out to the work site, or you can actually tow it. If you had a small boat and you were working in very shallow water, put it in the water in the harbour, and then just tow it to site and then release it to go and do its mission. So very low logistic in the sense that we can operate without dedicated large systems that we see bigger vehicles. Operations, as I said before, 5 hours will give you plenty of time to be launched from a CTV, go away to a survey area, do a grid survey, and then return to rendezvous with the CTV. We say that we need 2 AUV operators. Now, this is where you're sending this very expensive bit of kit out on its own. And it's not like an ROV where you've got a nice tether to keep you to recover the vehicle if everything goes wrong. So what we say initially is that we need 2 AUV operators to work the vehicle. This is because in the event of something going horribly wrong, it's a lot of pressure on one person. Now, what we foresee is that as we become a field resident vehicle, then the CTV crew will become very familiar with the vehicle, launch and recovery, and they will start to help to be the second man. And that's in the business model that we sell is for us eventually a single operator supporting the vehicle. Daylight operations, but not essential. The thing's fitted with enough communications and strobe lights that we can launch and recover at night, and it can obviously work at night subsea. That can work up to 3 knots current. You would adjust the line headings to go with the current rather than across the current. But that's a detail. Very quick to change out the batteries. It's just click in. 45 minutes to download your mission data. We can actually leave it in the water between missions and update the mission plan just over a Wi-Fi link. It is autonomous, but it is not intelligent. So it's got its avoidance procedures. So it will break off from a line, circle, and go and have another go at the line if it detects something in front of it. If too many alarms go off, then it's just going to abort the mission and surface. When it surfaces, it then basically does a ET phone home, and it phones the support vessel over an Iridium link, and then it passes on its status, why it surfaced, and then you can either tell it to sort of calm down, reset the alarms, and tell it to resume the mission, or if something's failed, you can go and recover it. Key thing though, which a lot of clients ask us about, can you go and do go and get us some pictures of the scour? We can't hover, so we're going past features at 3 knots. I get a lot of images, but we're not going to get video of a scour. The way that we can do the one-man operation is by putting a lot of the planning, mission planning, programming onshore, and that's sent out to the vessel over a comms link or just carried on a memory stick. And also doing the data processing onshore, shifting the data onshore. All right, so our big experience is in doing pipeline inspection, where everything's relative, but we're getting used to the renewables wanting everything in real world, absolute water depths and the like. Right, and then our processing is done in our Livingston near Edinburgh, where we've got our data processors who are very familiar with Gavia data, and we've got our own software package that lets us do the SLAM adjustment of the data to match to known features. So we've done various trials and demos for the wind farm operators and been matched against conventional survey vessel CTV operations. And in all cases, we've been able to show we've got a greater weather capability and we've produced better data, and we haven't taken up boat time in doing it. So this is, for us, a key market that we're selling into, not just in Europe, but also now in Taiwan and East Coast USA. And that's me.
Excellent. Thank you very much, Trevor. So we'll swap over now to Keith, and we'll do some questions and answers at the end. So Trevor, if you can stop sharing your screen, please, so Keith can share his. So Keith joins us from Blue Ocean Marine Services out in Western Australia, where he's the general manager. He's been with Blue Ocean for about just over 5 years. Prior to that, he has a link with Trevor because he used to work for UTech Survey, of course. And then he's got a background in metocean science, and I think probably spent about 12 years or so as a scientist, Keith, if I'm not mistaken. Educated at the University of Newcastle upon Tyne with a BSc with honours in marine biology, followed by a master's from University of Plymouth with distinction in applied marine sciences. Today, Keith's going to talk to us about lighter class AUV pipeline inspection. So over to you, Keith.
Thank you, Richard. I think I'm there. Okay, great. So yeah, thanks, Richard, and thanks, Jamie, for putting this together. So look, my presentation will be a little off topic. It'll be an introduction to the newly established Blue Ocean Marine Services. So this is a new JV. The exciting journey we've had proving up lighter class AUVs, specifically for pipeline inspection, and I will close with a case study with a twist. So without further ado, we'll get into it. I just move my slide. So Blue Ocean Marine Services was established in September of this year. This is born out of the group that I've been involved with for over 5 years, Blue Ocean Monitoring, and the Vertec group. So it is a joint venture. The reasoning behind that was that Blue Ocean Monitoring was set up on the belief that autonomous systems would revolutionize how we do things offshore. And it quickly evolved into more of an R&D hub. Blue Ocean Monitoring have been successful in setting up a few businesses. One of them you may have heard of is Blue Ocean Seismic Services, which is now owned by Woodside, BP, and Blue Ocean Monitoring, looking to revolutionize the seismic industry by designing and developing flying ocean bottom nodes. And we have a number of two defense businesses, and again, very much focused around R&D. So I guess the focus was lost on commercial survey delivery, and hence why this JV was created. We went with the Vertec group because they have a lot of synergies in terms of the technology they use and embrace, their geographical footprint, and their presence in the oil and gas sector. So together we've now formed Blue Ocean Marine Services, and it is a global survey services business. What comes with that, we're really focused on low cost and practical autonomy. There's lots of autonomous systems out there. We're only really looking at the shallower water market, what we call transitional water depth market. We have experience in autonomous underwater vehicles. We have some experience with autonomous surface vehicles. I guess traditionally our technology has been around the long-range glider platforms, both subsurface and surface, which has evolved a lot of our R&D ideas. We've always had a hand in metals and instrumentation, so traditional deployment of moorings, vertical moorings, etc. And now with the new association with Vertec and the Geo Oceans Group, we've really got world-leading experience in the deployment of ROV technology. And again, that comes down fitting the same glove is really around the lower cost compact ROV space. Blue Ocean Monitoring maintain their interest in Blue Ocean Marine Services, but they really act as our R&D hub. So a think tank, if you like. So that is something that we still use, and as technology evolves and the requirements evolve in the oil and gas space or in the offshore space, we can sort of have them as a support partner in developing some ideas in sensor integration, sensor development, etc. So what I wanted to talk about today was our investment into the L3 Harris Ocean Server Iver 3 platform. Our clients came to us with, and clients not just in the oil and gas space, we're looking for solutions in AUV. And at that time, I guess they were only really exposed to sort of the larger systems, and they were asking us, where we could go potentially with lighter class, low logistics AUV. There's a lot of yellow shiny tubes out there with props. We went through a fairly extensive and exhaustive process to find the technology that would suit our profile and would suit the applications our clients were seeking. There were some sort of higher level vetting criteria. I mean, safety, can a system increase your safety and lower risk? Are these systems reliable? For one, there's like I say, there's a lot of systems out there that, you do a lot of the trial and testing yourself. There's 300 of these systems predominantly used in defense circles. The efficiency of these systems, again, comes from the reliability and then the sort of flexibility of the system. But again, when you look at it just on a physical note, it's a small AUV. It packs a punch. 2.4 meters in length. That's with an extended payload, so it's actually 2.1 as a standard model. 45 kilograms in weight. The limitation that we have is depth, but the market we're targeting is a transitional water space from shore to 150 meters. It's depth rated to 200, and the modular aspect just opened up all of the applications that we were seeking to put a tick a box in. So going through this, specifically around pipeline inspection, we invested in the IVER 3 in the middle of last year, and we put it to test immediately on a project here in Western Australia, really as a proof of concept. That has evolved. We have a fairly rigorous in-field testing program here at Blue Ocean Marine Services in waters off Perth. I mean, really for us, we were looking at a number of key success criteria for this application. The obvious one being lowering cost. We were looking at, can we reduce operational schedules or be opportunistic and flexible in terms of schedules? So if weather windows limited or opened up opportunity, we could go for SimOps, for example, where we can deploy and be ready in short timeframes. From a logistical standpoint, a big thing with AUVs and ROVs traditionally is getting things to site. So looking at that, the labor effort, the intensity around logistics, and then obviously then you're looking at risk. So whether that be a project or financial risk, environmental risk, and of course, human risk. That's all well and good if you can lower those things, but if you can't maintain status quo in terms of quality, there's no point trying. So if we can satisfy that or raise the quality, when I say quality, accuracy, resolution, accessibility of data, well, those are kind of that's the success pathway, and this presentation kind of goes through that based on the projects we've conducted now commercially. So with cost and Trevor, you touched on a few of these points, and I think there's some similarities between the systems. You know, we were looking at a lower hardware cost. So cost was a key part of, if we're going to outlay on these systems, you know, what are we competing with, and which obviously equates to your project fee. So it's quite an attractive entry cost for acquiring these systems. When you actually put these systems to test, then you're looking at a lowered staffing requirement offshore. So again, 2-person, 3-person in some circumstances. We're looking at smaller vessel operations. There's no pre-project fabrication on the vessels. There's no mobilization calibrations. We hit the vessel and we go. So this falls down to rapid mobilization and demobilization, which is particularly attractive to our clients. These systems, and this mobilization and demobilization will come up in a number of slides, so I won't harp on about it too much. But you know, being able to get to site, these systems aren't ITAR restricted. We can put them on passenger planes. We can put them in the back of the truck. They are ready to go in the workshop. The small size means that you've got reduced freight costs. So you can see in the images here, is a vessel we used recently in Indonesia. And on the left-hand side, to the right-hand side, this is part of the proof of concept where we're testing shore launch. So 45 kgs, 2 people waded into the shore, and off it goes. So looking at schedule, again, falling back to rapid mob and demob, the image you see on the left-hand side is a fully loaded system. That is an AUV, an ROV, and a full USB positional spread. So typically we wouldn't take that much with us. But again, back of a truck, and we head north to the Pilbara. We could be there in a day, and we could be on the boat and basically starting project prep in transit within 24 hours, which feeds quite well into the cyclonic season, which we have, which has just started. So again, so rapid response, emergency response is another market sector we're looking at. You say these are deploy-ready systems at our facility in Perth. We have 2 systems, which allows us to do multiple AUV deployments. So this is hot swap or leapfrogging AUVs, or actually concurrent, putting 2 AUVs to work at the same time. The 2 AUVs obviously gives us redundancy, but we carry full sets of spares on board. In terms of logistics, like I said before, it's very, very simple. Ready to go systems, palatable, manhandleable systems. The image to the left was on the proof of concept where we were actually operating in SimOps. The vessel demand was high. Sometimes we had to march the AUV from one side of an island to the next to either meet the vessel or shore launch. there's no complexity in terms of the fabrication. Our launch and recovery systems are simple. I mean, we're talking about a crane arm and a couple of strops. We have a number of ways of deploying for different vessel types, but this can quite literally be over the side of a rib. Risk is a big one. So we've proven that on our projects we can lower these risks significantly. We talked about the staffing, people offshore. It is what the offshore industry is trying to do to reduce staffing requirements offshore. We rely on a team of 2 to go with the AV per 12-hour mission. We're not restricted to daylight operations. We can go 24 hours, which obviously increases your staffing input. But again, small, compact, small team. The team are fully trained. There is no separation between the people working on the AUV in the workshop to the people who are deploying it in the field. So we can troubleshoot in the field. We offer the redundancy with the AUV. Each project will have an ROV, a compact class ROV go with it. The USBL systems are the same. It has a cutting tool and a manipulator. So we can, if for example, the AUV was to get caught up in seaweed or fishing line, we can go and recover. That said, the AUV's got smarts inside it. It has a safe return path protocol whereby if it does get into trouble, it will surface and it will navigate itself back to a predefined waypoint for recovery. It's got a collision avoidance system. This AUV is not going to cause any damage to any subsea infrastructure, but we're a little bit concerned about it getting damaged itself. So it has that forward-looking sonar for collision avoidance. And then we go from an environmental point of view, it's battery operated, rechargeable battery operated. We are using smaller vessels. We are hoping to reduce schedules. So it all feeds into the zero carbon intentions of the oil and gas industry. And then from a human point of view, we've proven the system time and time again, over 100 deployments, safe handling, launch and recovery with no glitches. Quality, of course, needs to be maintained. So we have on board the Ivor, we have a interferometric system for Bathy. It's an EdgeTech 2205 system. It concurrently records Bathy and side scans. So in processing the data, you're going from the same source point. We've put first Ivor to have a digital camera on board, and we've also put on the extended payload section, which allows us then to put in water quality instrumentation. And we use that very effectively, just profiling for water quality to 200 meters. In Indonesia, we were just seeing a sort of ridiculous amount of efficiency compared to what would be a manual operation lowering profilers into the water. We've found in our deployments, and it's a continual process of improvement, but we can achieve positional control and stability in shallow water environments. And when I say shallow water, again, it's from shore out to about 100 meters. In terms of pipeline inspection, we need to get on assets and we need to track assets. So if we've got good information on where the assets are, these things are particularly effective in capturing the data we want with the GPS fixes seeding the INS and DVL system. The swath width on the EdgeTech system is extremely forgiving. We haven't had a situation where we've fallen out of high resolution side scan for any of our projects. And then our data accessibility has been improved with the development with L3 Harris. So typically we're looking at sort of 45 minutes turnaround times, downloading the information, getting that information to our surveyors on board to check what has previously been collected. So when I say there's a case study with a twist, this is it's worth talking about this project. One, because it's fresh in my head, we've just come off the project. But it was a project whereby the client needed to mobilize quickly. He wanted what they wanted. They were looking at 2 scopes. One scope for AUV, coming back from AUV, and then mobilizing a second scope to an ROV contractor to then go and investigate the findings of the AUV. So we actually looked at an integrated approach. So with the Vertec group comes a number of companies, one of them being GeoOceans, who just picked up the Subsea Energy Awards, Subsea Energy Australia Award a few weeks ago for Company of the Year. They have a fleet of about 20 compact class ROVs. So we got together with them and approached this in an integrated way. At a high level summary, really looking at the AUV to fly the radials, to identify freeze spans and any other anomalies, and then the ROV to go in and investigate. So it was 90 kilometers of pipeline. They wanted both low and high resolution side scan. Bathy wasn't a requirement, but it was recorded and it has been processed. They wanted onboard processing and then the ROV to be deployed whilst the AUV was underway on its next mission. So a fully integrated, one vessel, one mob, one demob, get the job done and come home. So in terms of those sort of 4 bullet points, we just go through those. This is the vessel we operated off. So that's the full ROV, AUV spread. The containers on board aren't ours. And yeah, so I mean, it was putting a full operational team together. This is only for daylight operations. We could have accommodated 24-hour ops. It wasn't necessary given the short time frame of the project. Our AUV was put to task at approximately 8 meters altitude with a pipeline offset of 11 meters, which gave us sufficient forgiveness in the positional control to pick up what we were looking for. Our GPS fixes, so the AUV surfacing to get the fix to seed the INS and DVL was typically around 1,700 meters, and our AUV speed was traveling at about 3 knots. So with the side scan, we were to pick up 6 flow lines. They varied in diameter between 4 and 14 inches, and then 9 umbilicals, 4 to 5 inches, which is a little bit challenging. We were in 60 to 90 meters water depth. We adopted a 2-pass approach on the pipeline, so 90 kilometers of pipeline turns into 180 kilometers. We were able to achieve that in 17 AUV missions and total water time 23 hours. With respect to the onboard processing, so we had a 3-man team rather than a 2-man team. We had a data processor on board. The idea was to be able to QA, QC and process the data for target and feature identification for the ROV to inform the ROV scope. So you can see in the image there, lots to get involved in. 90 kilometers of pipeline, 271 free spans, not only in the flow lines, but also the umbilicals. There was various infrastructure that we had a look at outside of the scope, anode skids, Christmas trees, etc. And then we identified other, I guess, anomalies of interest in close proximity to the pipeline. And this is where GeoOceans came in. They were under a USBL system with the SAB CI Falcon. Blue Ocean Marine Services provided the positional spread and the positional services for their ROV. And whilst the AUV was running the radials, running the pipelines, then the ROV was getting wet, doing the investigations. So it really was a integrated sort of hand-in-hand type operation. It was very effective. There was no downtime associated with our SimOps. It was managed very effectively. The beauty of the ROV is you can investigate your perception from what is quick processing on board of a free span. And we say free spans of 1 meter to 35 meters, and a lot of them, the ROV can go in and with certainty give a general visual inspection and confirm that the free span exists, but also then to physically measure the length of the free span and height. Now that ROV was equipped with other tools, gauging tools. They had UT on board, they had CP on board. So these are additional scope items that were brought in, but just outside of this presentation. I wanted to focus on what we do, not what GeoOceans does. But it was really effective. So the entire scope was completed on time, 100% deliverable, and full client satisfaction. This project was born out of a previous project. This is the second in a run with this client, where quite frankly blew them away with the management of these systems, the agility and the practicality of getting to site, getting the job done, and coming away was impressive. And yeah, long may it last. But I think, again, it's to look at the IVER 3 AUV as a very formidable system and can be used independently. But what we want to do as a business is to look at other compatible technologies, and as sensors get smaller, faster, and more power efficient, bringing them onto these systems or other systems. We're fairly agnostic when it comes to the platforms. This just happens to be what we think is a superior platform for pipeline inspection. So that's basically it. Other applications and services we're interested in, I'm not going to go through them. We are mobilizing for a cable route survey where we're going to tow a magnetometer over quite an extensive area with the IVER 3 system, and that is a utilities project. We have another pipeline inspection coming up, again, on the back of the success of the others. We have a Met-Ocean survey where we put the IVER to task to do this water profiling work, and that has actually then opened up work in the Met-Ocean space, where we're putting in deep water moorings and doing some environmental monitoring up in Indonesia. We're using the IVER 3 AUV for produced formation water monitoring, so plume monitoring. So as the PFW is discharged pre, during, and after, we can use the IVER 3 very quickly to look inside that plume cyclicking transects to understand plume dynamics. And one thing that has come up recently, we've just entered cyclone season down here, which is an exciting time for everyone. And the fact is we've got the two AUVs sitting here, ready to go, ready to be put on a truck and be in the Pilbara in 24 hours, or certainly on a truck or on a plane. That market's opening up for us. So I guess that's a kind of summation of where we're at. Like I say, Blue Ocean Marine Services has only been established in September, so we're still getting up and running. But there's a pretty hefty project pipeline ahead of us, and it's exciting times. Pardon the pun, but the pipeline. But thanks for your time, and I will close off there.
Excellent. Thank you very much, Keith. So up next, we've got Chris Eccles, who's the Business Development Manager for Survey Services within Oceaneering International. And he started his career some 28 odd years ago in the oil and gas industry as a diver. From there, he's migrated into the equipment and rental market with Ashtay Technologies, and most recently, he's joined Oceaneering International and supports the global business development for geoscience, survey, and positioning, and the CNAV product lines. But today, he's going to talk to us about something kind of interesting: the next generation subsea vehicles and using autonomy to increase the efficiency of operations. So, Chris, over to you.
Thank you very much, Richard, and thanks to the Oceanology Section Committee for choosing the paper today. And Keith, I can tell you, if your cyclone season was anything, or is going to be anything like our hurricane season that we're just ending with, hold on, because 2020 has been a crazy year for us. So just there you go. Thanks again. Again, my name is Chris Eccles, Business Development Lead for Oceaneering Survey Group, so based out of Houston. The Survey Group is one part of a newly formed subsea robotics unit within Oceaneering. So we've got the ROV, survey, and tooling departments now within our group. Today's presentation is going to be about the next generation autonomous underwater vehicles, and I'm going to explain to you what we're currently developing. I'm going to explain how we're going about doing it, and really what the future of the subsea vehicles are going to be looking like coming from Oceaneering. So today, the Oceaneering Freedom autonomous subsea vehicle combines work-class functions of an ROV with the speed, range, and maneuverability of a ROV itself, but it really is in a total autonomous package. So Freedom can operate in two modes: remotely piloted with a tether. And we've got a pilot on the stick providing real-time control to it. Then we have an autonomous or tetherless mode, no human interaction whatsoever. Freedom has a working range of about 200 kilometers per mission. Depth rating 6,000 meters, as they're telling us, and then we've got a maximum speed of 6 knots it can travel at. So our typical survey speeds are going to be around 3.5 knots, maybe a little less, depending on the resolution that we need. And then survey altitude, we run about 1 to 5 meters for inspection, like pipeline inspection type stuff, or reconnaissance. We could, be up around 8 meters or so. This system is designed for deployment for up to 6 months. We haven't done that yet. We're still in trial phase, but that's what all the systems, the thrusters, the payloads, everything has been designed for that type of duration, being subsea. We've got numerous variations of the Freedom platform. It can support inspection work, intervention work, survey work, or resident in-field systems. So today, I'm going to be talking about specifically pipeline inspections. So across all of those platforms, we have one commonality: the thrusters, the batteries, the computers, all the same as in our supervisory control software that we're running. Currently, we have or manufacture within Oceaneering multiple types of autonomous vehicles. We have land-based AGVs, or automated guided vehicles. We do autonomous underwater vehicles, or AUVs, and then obviously the work class ROVs that many are familiar with us by producing. So focus today is going to be, again, on this top left slide, and I'm going to talk about the machine learning and artificial intelligence packages that we're running. So the software operating system that's in this is system agnostic, means there's so it supports a variety of types of missions that we can throw at this. So the agnostic approach allows for easy rollouts to that entire fleet that I just talked about. So we change one aspect in a package, and that can roll up to all the different ones. So we're all on that same path. Our current Freedom platform, again, I'm going to talk about today, is that pipeline inspection system and how we're going about doing that at this time. So we're typically finding our pipeline inspections are done with AUVs or ROVs. That's quite commonplace these days. The difference between our Freedom versus conventional technology is pretty huge. A typical AUV, is going to fly between 5 and 15 meters over the seabed. They don't hover, as it was mentioned earlier today, and they don't stop over a pipeline. They don't intuitively, investigate an object if something has come up in their view, and they don't park themselves into a garage automatically. So that is really the fundamental difference of what this Freedom platform is doing versus the conventional AUV systems. So our goal was to develop all that. Plus, we needed to operate 1 meter over the seabed. 1 meter is normally way too close. When you've got this some distance like that over top, you need some serious machine learning and artificial intelligence algorithms to be running. So that's 2 must-haves we asked for: keep the Freedom and the subsea assets safe, and to track the pipeline reliably. So because of that, flying low brought its set of challenges, mainly bumping into things. A big no-no in the industry. You don't want to hit a customer's asset. So let's not forget, lower the altitude, you get much better resolution, but you have a much shorter reaction time to maneuver out of the situation. So the supervisory software control enables this safety to take place, and that's running an array of sensors 365 degrees around the vehicle itself. So effectively, we've built a platform with enhanced situational awareness. It's packed with machine learning. It can recognize pipeline features, detecting free spans on its own, looking at depleted anodes and analyzing those, identifies, different crossings where mattresses would be, alerts on anomalies, which then can go and trigger other missions for it to go and investigate. So when you have this ability, you essentially eliminate the need for hiring another vessel to come out and do a whole other project. So no chartering, no ROV crews required. You don't have to go find a survey contractor. Keeps that carbon footprint down, and then the HSE environment all remains safe and are in the green. So that's one of the benefits of having this automation that we're running. So traditionally, inspections ROVs, as I said, are flying about 5 meters or so. The faster the uprate rates, the systems on board enables us to monitor what's going on. So when it does identify something like an object in this pipeline, for instance, that it was flying over, the machine learning kicks in and it can stop, hover, kick on the 3D lasers, turn on the video system, take high def images of it, because all these sensors are working with the onboard processing system. So I've got this video here. This was taken in our living lab in Norway. Let me just click the play button there. So this is in Tau. It's in a fjord not far from our Norwegian office. So we've been performing in-water tests for nearly 2 years now, I would think. And this living lab has quite a unique place because it's got a plethora of subsea assets all along the seabed. It's kind of built into a fjord, so it's pretty protected from the environment, but yet it's in deep water, shallow to deep water. So what we have is like an exact replica of what it would encounter in a real live offshore environment. So the testing has been great. What's become apparent is that the autonomy isn't easy. It takes a tremendous amount of programming and time to get this right. Adjusting logarithms for real world applications is constant. This video is going to show you also how we launch and recover the Freedom system. So the sensors on board, they've got the 6 degrees of motion with the thrusters, and it allows itself to come in and dock into its own garage. This allows us to deploy it below the ship's hull in a safe distance, away from the propellers and thrusters, and then it can go out of the garage itself, fly, do its mission, and then return back safely. So that has been a bit of a game changer. We don't have the need for strops or anything, no human interaction. It does its own, and the crane will lower the basket or the garage down all through the heave compensated crane. So it's all good and safe, and people are out of harm's way. So this is a picture of our graphical user interface. The data is uploaded and downloaded from the vehicle, health status, mission information, power levels alerts that it detected on its project, or any discoveries are all collected and analyzed here. So that's it's a lot of information coming through, but it's quite useful, the feedback. So this September, we launched the first docking station. So this is Freedom actually going in and docking on this platform. So this set in motion a whole longevity issue of what AUVs can now do subsea. So that was a big hurdle in our testing to get this accomplished. We convinced ourselves, but not only ourselves, but our clients, that this is now ready for in field use. So now that we can dock, we can charge, we can upload the data, and this charging system acts like a new generation cell phone or a Apple Watch or something. It's got an inductive pad, and as it sits down, it charges the batteries that way. I'm not going to get into all the physics of how that works, but it's just, the same as cell phones are working these days. So once it's charged, it's got its mission communications. We can upload and download information through this charging pad. It knows what it's doing then, and then it can head off and complete this mission. And then back and forth it goes. So over time, and once these missions are done, the package can be returned, or if it's permanently installed on a subsea asset, we can then just leave it there for like in use or in-field operations. So that's why that was designed. So that was a permanent type install in the future. But what we're also looking at is the Liberty Enhanced ROV system. So this is a combination of old technology and new technology. The ROV itself is pretty much a traditional ROV. It's got a traditional pseudo traditional cage around it. It also has a battery bank, which is obviously new. That's providing power to the sub and to the sensors on board the ROV itself. Also, communication to the surface. This is quite interesting. So we once it's deployed over the side by a ship, there's a communications buoy that comes up to the surface, clicks into the 4G cell towers in the area. So this is great for North Sea applications where you do have that kind of connectivity out there. So the EROV is completely on its own. Once it's deployed and set up, this whole platform is lowered into the water, the vessel can go back to port or go off and do another project, whatever it is needed to do. But the key here is we're in control of this entire ROV package from our remote control monitoring systems. We've got them in Morgan City and we have them in Norway, where we can actually take control and operate these ROVs. This isn't a conceptual thing. We've been running this actual operation now for about 1.5 years. So it is actually deployed in the North Sea working today. So what we're looking to do is use this technology from the Liberty EROV system and then combine that with Freedom. So when you start doing that, you get yourself off that tether. So the Liberty EROV would typically have like a 500-meter tether on it, so it can move around its garage there. Well, with Freedom and the autonomous platform that we're running, we don't have a tether. So then all of a sudden you have a much greater area that you can cover. Opens the door for much more cost-effective solutions, and it also, once it's charged up, it's running on its own accord. It can bring back so much more data on that real-time monitoring. Great for inspection type platforms. So I think the neat thing is it's an entire mobile solution. It's nothing permanent installed. Again, it's project specific. We can come in, we can drop this thing, it can go do its project, and then it can be recovered at the end of the job. So that's where we're heading with this. So some Freedom examples here of what we're talking about. It's a whole new application. We have the charging station, we have the communications upload download facility now that's developed. So once that's done, the doors open for this whole world of autonomy with our Freedom platform here. So there's nothing, again, permanently installed. Everything is temporary. Missions are uploaded, the vessel or the vehicle goes out. We can cover, as I said earlier, about 200 kilometers per mission with this system. So if you look at that, that's about 1/3 of the greater London area on one project. So with three missions back and forth from this garage, we can effectively cover the whole of the London metro area. So that really changes things. So I guess really in summary, the autonomous vehicles, they do have a ways to go. Some of this is conceptual, some of this is actually being used in real life. So we're beginning to blend it all together. The vehicle itself, as you see, is operating. It's about to go into its first real sea trial in the North Sea. It should be very soon, probably by the time this airs at Oceanology, that will have occurred. So continually, we're developing the packages with the charging systems are being improved over time. The algorithms with all the data we learn from every project, it's all being collected, analyzed, and then we're developing, as we go along. So, ultimately, where's the future of subsea robotics? It's going to be a combination of, man-in-the-loop operations with a greater reliance on autonomy. There's still going to be that that interaction, but we're quickly getting to that point where it goes on itself. So that's really a quick summary of where we're at with the Freedom and our autonomous system. So hope that helps you out there.
Very cool. Thanks, Chris.
Sure thing.
So our last presenter this afternoon is Adam Mara from General Dynamics Mission Systems Bluefin Robotics. I suppose to give it its full title. Bit of a mouthful for that title there, Adam. So Adam's a Senior Strategy and Business Development Manager for Undersea Systems for GD, and has expertise in development of and fielding unmanned underwater vehicles and related technology across the defense, industrial, and academic markets. He's worked in partnership with operators to evaluate UUV capabilities and future applications for more than a decade. And he's got a Bachelor of Science, an unlimited United States Coast Guard Merchant Mariner's license from the Massachusetts Maritime Academy. He also got an MBA from Sawyer School of Business in Boston a few years ago, and has served as a navigational officer aboard US merchant vessels. But this afternoon, Adam's going to talk to us about complex environment operations of Bluefin Robotics unmanned underwater vehicles. Adam, over to you, please.
Great. Well, thank you. And thank you to everybody in Oceanology International for the opportunity to present our Bluefin Robotics UVs and some of the marine operations that our team has conducted over the years. Again, I'm Adam Mara. I'm a Senior Strategy and Business Development Manager with General Dynamics Mission Systems. For over a decade, I've had the joy and pleasure of working with Bluefin Robotics UUVs. Today, our presentation will focus on UUV operations conducted around the world and lessons learned from operating UUVs in these complex environments. As this team, certainly knows, operating subsea equipment has unique challenges. For background, we'll discuss the marine operators that help design, test, and evaluate every Bluefin Robotics UUV. We'll then focus on specific UUV design considerations from an operator's perspective. From there, we'll dive into specific operations the team has conducted over the past year or so and lessons learned from these operations. At General Dynamics Mission Systems, we believe our operators are some of the best trained UUV operators in the world. Every Bluefin Robotics UUV is rigorously tested at our Oceanside facility near Boston, Massachusetts, in the United States. Whether the bay is covered with ice, or the vessel's so hot that you can cook an egg out on deck, each and every UUV is tested by these operators. These operators are critical to our product development process. Robust testing is necessary, and we are sending equipment down to the bottom of the ocean. Our team travels the globe aboard vessels of opportunity, supporting and training delivery of over 7 different UUV platforms. Today, the operations we'll discuss feature the 2-man portable Bluefin 9, the open architecture and payload agnostic Bluefin 12, and our workhorse Bluefin 21 UUV. These are the platforms that our operators test almost every day. The Bluefin 9 is a small diameter UUV for littoral and nearshore operation. It includes the Sonardyne Solstice multi-aperture side-scan sonar, environmental sensors, and a full navigation suite, including an INS. The Bluefin 12 includes these same sensors, but also has an option for an open payload architecture. It currently has a greater endurance than 24 hours. And the Bluefin 21 is used for a wide variety of applications and is rated to 4,500 meters. As mentioned, our operators are critical to the design process. Every day, these operators are using UUVs off of New England. And as some of you know, this is an area with hundreds of thousands of lobster pots. Each pot sits on the seafloor and has a buoy that floats to the surface. Years ago, almost 2 decades ago, earlier in the product evolution, our team designed and developed a ducted thruster to avoid snagging lines or seaweed. Over the years, this design and this ducted thruster has helped us optimize speed with precise dynamic control. The ducted thruster oscillates in 12 degrees in every direction, and that's what actually is controlling the vector. We do not have dive planes on the side of the vehicle. This allows the vehicle to avoid snagging lines or seaweed. In addition to that, each component of the Bluefin Robotics UUV is designed for in-field maintenance to maximize operational time on station. To reduce processing time, as the team knows, our team developed a quick way to qualify and review sonar, camera, and environmental data collected by processing data while the vehicle's still in the water. The team then collects the vehicle, and once the vehicle's recovered, they use a removable data storage module. The removable data storage module is swapped, the batteries are swapped, and the vehicle gets back in the water. And so this whole evolution only takes about 20 to 30 minutes. And so over an operation, this optimizes the UUV's time in the water and increases the amount of data generated. As the vehicle is in the water more, it creates a greater area coverage rate. The advantage to this type of approach is that these operators literally plug in the drive into the laptop or your post-processing station kit, and then they can view the sonar waterfall immediately, literally minutes after the data was collected. We also have the ability to send clips of data over acoustics while the UUV is underway, using something that we call the topics infrastructure. As a direct example of how at-sea operations, customer feedback, or feedback from our operators on a daily basis fits into our product development process, I've included the Bluefin 12 architecture here. Every LRU can be swapped in the field. This includes the ducted thruster, our antenna, swappable batteries, our removable data storage module, the payload itself, the forward-looking sonar in the nose section. Every component was designed to be flown around the world, similar to other systems, via air cargo transport. We've had some great business cases and last-minute air freight to highlight why this is so important. While this layout shows the Sonardyne Solstice multi-aperture side-scan sonar, the vehicle also is offered with an empty payload section. One of the things that's unique to our system is that our payload interface specification is actually found on our website. So today, what we're doing is we're going to review some of the marine operations conducted around the globe in challenging environments. Really, our operators are the ones that are put in some very unique situations, and these four examples highlight some of the challenging environments that they're operating in. This includes high current operations in the Solent, the United Kingdom, shallow water operations in varying salinities in the Patuxent River, Maryland, in the United States, under ice operations in the Arctic Circle, and some highlights from some of the work our team is doing in Australia as part of the SEA 1778 program. Many of you may be familiar with this chart. As you know, the Solent is a challenging place to operate subsea technology. Tidal currents are dynamic in nature and present challenges to planning and executing UUV surveys. As a previous merchant mariner, while at sea, we used to believe that a single knot of current has the same impact or force of 30 knots of wind. The Solent can reach greater than 3 knots, which is the equivalent force of a hurricane. Last November, the team was fortunate to collaborate with the UK MOD, Maritime Autonomous Systems trial team, aboard their USV to operate and test our Bluefin 9 in the Solent. While working with MAST, our Bluefin 9 was deployed aboard their USV to evaluate the quality of data generated by UUV in high current environments. The Bluefin 9 was tested with its integrated navigation package, which included Nortec DVL and Ixblue INS, and the Sonardyne Solstice multi-aperture side-scan sonar. To test how best to generate data with the UUV, our team planned a survey that approached the prevailing current from multiple angles of incident during the ebb tide. This meant having the UUV swim in multiple headings to evaluate data quality against the current. Whether it was with the current, against the current, or broad to it, our hypothesis was that the UUV would capture the best data by operating in speed over bottom configuration. The UUV mission planning software allows users to plan a mission and target the optimal speed for the sonar survey, adjusting the tailcone propeller RPM to meet the optimal speed through the water against the current. Our team anticipated that the UUV would keep a constant speed against the current while reducing crab angles to the intended track line and would generate optimal survey data. However, our goal for this operation was to counteract the dynamic current in varying current by adjusting the propeller's RPM to keep the intended and optimal speed for the operation. What we actually found is that the ducted thruster increased or decreased RPMs. So as the ducted thruster increased or decreased RPMs, it slightly impacted the UUV's roll stability on certain headings. The lesson learned in the UUV's team solution: switch our mission planning configuration to a constant RPM setting for the thruster. This allowed a constant propeller thrust as the UUV swam on each heading. The trade-off resulted in a slightly higher crabbing angle as the UUV approached the dynamic current. Our team thought that this would be a challenge for side-scan sonar data generation. Historically, increased crabbing angles skewed data that was collected by side-scan sonars. Upon recovery of the UUV, the team reviewed the data and were delightfully surprised at the data generated and continued to operate the UUV in the same dynamic current. The combination of high accuracy navigation package and multi-aperture sonar produced data in a dynamic current with little data degradation. Of course, due to the crabbing angle, the overall swath width was slightly reduced by a few meters. However, the overall mission was pretty successful and showed little skewing of the data. This was a great advantage to UUV operations working in this riverine environment. This image represents side-scan sonar data that was generated in the operation. As you can see, the UUV was swimming at with a crab angle of about 20 degrees in a cross current, trying to maintain its planned survey path. For those of you who are not familiar, the black line in the middle of the data is what was called the nadir. This is typical for UUV operation as the area directly below the UUV. As shown in previous presentations, additional gap filler sensors can be integrated to cover the nadir. However, there was not a gap filling sonar integrated for this operation. What this image shows is that at the outer range, usually about 100 meters aside, so on the right side of the screen and the left side of the screen, the data is only skewed slightly, reducing the swath width by only 4 to 5 meters. To further illustrate why the team thought this data was remarkable and unique, each image represents a different heading into the current. The object in the middle of the image shows the vehicle swimming at various crab angles. There's incredible detail in each image. The Bluefin 9 produced clear imagery without skewing or distortion in each heading that it swam. The sonar illuminated the object in each image, allowing users to view the object with greater fidelity and determined the object's height off the bottom through the shadow that was presented. This was a great success when compared to conventional side-scan sonar that's typically integrated aboard UUVs. Current can have a dramatic impact on data generation. However, what was significant and remarkable about this operation is no matter which heading it was, you can see that this block was highlighted very well. Our next operation takes us to the shores of the Patuxent River, a tributary to the Chesapeake Bay in Maryland. UUV operations in a riverine environment can present some really unique challenges. For this operation, our team was challenged to operate the Bluefin UUV in very shallow water with varying salinity in high turbidity. Due to the varying salinity caused by freshets, for a couple of days prior to this operation, it had poured and there was a lot of rain. And so the team had to adjust our buoyancy calculations and account for operations in both fresh and brackish water. The team was pretty confident that because of free-floated architecture, we could adjust to the buoyancy and the salinity values as the vehicle swam, but it was a challenge and it certainly was a risk when operating in a shallow environment. We feel that one of the advantages to a free-floated architecture is that the UUV has a greater tolerance for varying salinities. In this mission, the Bluefin 9 was run again with the sonorized Solstice in a typical lawnmower pattern in very shallow water. And as you can see, there was a lot of mud in the Patuxent River. Depth on this chart is shown in feet, which means that the team only had a few meters of depth in some of the areas that we actually operated. So operating in very shallow water presents some challenges when conducting side-scan surveys. For many sonars, there's an optimal height off of the bottom for the sonar to swim. If you're too close to the bottom, data can be truncated or segmented too close to the surface, and you can generate some surface effect or multipath. For this survey, we planned the mission to have the UUV swim as close to the surface and at approximately 5 meters off of the bottom. Our operators were elated to see that the UUV's ability to generate data in this shallow water environment with about 100 meters of range on each side. So the swath width was about 100 meters on each side. As you can see in the upper third here of the data, you can note that there's a remarkable data bottom change here, and so it goes from really mud into something that looks like shale or some shells. And then in addition, as you zoom in on the imagery in the bottom left of bottom left and bottom right of the data, you can see that there's some significant scouring on the seafloor from some marine life. So later in that same operation, we tried a different spot, and so the team then conducted a survey of a known wreck. This was an equally challenging environment, and part of the reason was it was a really tight channel. There was definitely some traffic, and there was because of the way the channel is configured, there was a very dynamic current with close walls, and then you had the wreck itself that was sitting on the seafloor. Our team was able to plan a flawless mission. As you can see, the USS S-49 sits proud on the shallow seafloor. So there's a lot of marine growth and things that are hanging off of it. So the team was able to drop the vehicle in the water, and after the first survey leg, they quickly recovered it and pulled the removable data storage module while still on station, just to see what type of data they were going to get. The image that you see was of the USS S-49 was generated. And this was generated in real time as the vehicle was serving. And the operators were able to view this within about 5-10 minutes of actually surveying this area. As you can see in this image, the S-49 mast, gear, and deck are illuminated very well. This was a great example because in this really unique riverine environment, you're still able to generate data with a UUV. As with every operation, there were many lessons learned on this one. This operation highlighted the ability to use a two-man portable free-flooded UUV in a shallow and congested riverine environment. Throughout this operation, our team was training both some new operators and some familiar with previous generations of our vehicles. In this challenging environment, these operators were able to plan, execute, and conduct maintenance over several days without hesitation in order to generate this useful data. It was a great business case for us. This type of mission had been a challenge for UUVs in the past, and there's some great examples of conventional side scan sonar that have been used on this actual wreck. We think that the real reason, or that this highly accurate data was generated in this suboptimal environment is really because of the sensors that we were using and the combined system, so that you can actually conduct UUV operations in the riverine environment. As highlighted in the two operations we've discussed, our team is used to operating UUVs in a wide variety of challenging environments around the globe. We try to put them through their paces. Last spring, the Bluefin 21 was used for some under ice missions as part of the ICEX 2020 operation with the US Navy. As shown in the image in the upper right-hand side, the vehicle was launched and recovered through a simple hole cut in the ice up in the Arctic Circle. So from a logistics standpoint, you can imagine the challenges that result with this. One of the lessons we learned during this operation is that as the ice flow is constantly moving, and so the team had to alter away from traditional navigation. Instead of using a DVL with bottom lock, we had to make use of a surface-based LVL. The Bluefin 21 is also the UUV platform that Knifefish is based off of. Knifefish is a medium class mine countermeasure UUV intended for the deployment from the US Navy's littoral combat ship, and also other Navy vessels of opportunity. As you can see on the bottom right-hand side, our team has also been down under in Australia, near Keith's home, delivering and testing some Bluefin 9s and Bluefin 12s for Thales as part of the Royal Australian Navy project SEA 1778 project. For over 2 decades, our team has been testing and working with Bluefin Robotics UUVs in unique and challenging environments around the globe. At sea operations like this one's help our team design and develop robust UUVs that meet our customers' needs of today, but are adaptable for new technologies in the future. So whether it be a new sonar or a new sensor, we want to try to remain future-proof, and that's a challenge in itself when conducting marine operations or swapping sensors in the field. Thank you for your time. To help put our operations in, we've discussed in context. We also have a video here and a link that gives you a full operational view of the Bluefin 9. We can play it, or and if anybody has any questions, please not hesitate to ask. Richard, I'll probably we can move on to the next section.
Okay, you sure?
Yeah.
We can play it if you like, but okay. Well, thank you very much, Adam. Let's have some questions and answers then. So thank you to the panel there for the presentations. I have certainly found it fascinating. Even having been in the industry for a while myself, I'm always keen to learn what other people are doing and how they use their equipment. For me, perhaps the biggest thing for me in the AUV industry, Adam, pardon the terminology here, but the differences in what we call things, the biggest thing for me is autonomy. And a few of you have raised some interesting questions or posed some interesting challenges around autonomy. I'm going to start, if I may, with a cultural question that kind of applies to all of you. And that's, what is the biggest challenge that you've faced in actually enabling end customers to trust an autonomous product? Trevor, let's start with you, because you went first on the presentation. What challenges have you faced getting your customers, your end users, to actually trust the data collected by an autonomous product?
My problem is specifications. Right, that a specification for a project can be written for pole-mounted multi-beam, as I discussed in my presentation, or can be written for ROV, with an emphasis on video images of a pipeline. And we have to go to them and say, well, do you really need video images of the pipeline? What happens if it's bad viz? Then you're not going to stop the survey. You're going to keep going and just rely on your acoustic data. So we go, well, let's just pretend the AUV has gone and done your pipeline survey and there was bad viz throughout. Therefore, you weren't getting any video. So why do I need a video camera on my AUV? So short answer is the biggest challenge is specifications.
Okay, so the sensor selection then plays quite a role in there. And Adam, on the Bluefin vehicles, you've got the Solstice side scan, multi-aperture side scan, which is, it's a really good side scan, but could be considered non-traditional. Do you see any challenges in getting non-traditional sensors accepted by the end users compared to, your usual side scan sonar and multi-beam echo sounder?
Certainly, as this team certainly is aware, unless you see a vehicle operate, it's really challenging to convince people to change over from typical methodology. So swapping from, say, a towed sensor to a UUV can be a challenge, but once people are able to witness the operation and see a vehicle operate, and then see the quality of the data generated and compare it to those types of operations, I think it's a significant advantage. So really it comes down to how many vehicles are out there in the world and how do we get people to see more of them.
Indeed. There are, I think at the last count, there are something around the 2,500 to 3,000 vehicles that have ever been built in the world. It's really difficult to actually know. The RAND Corporation last year produced a paper that said there are about 178 different types of UUV, AUV, cruising class vehicles. Now, Chris, you're bringing something very different to the table with a vehicle that can hover and cruise and stay subsea resident. Now, I remember speaking at Subsea Survey in Galveston in 2010 about what the future looked like, and actually about what the future looked like for 2020. And we back then, 10 years ago, crikey, we're all talking about subsea resident capability and hovering vehicles and tetherless autonomy for inspection. And there was, to say in the auditorium, there was perhaps a little bit of disbelief that it would be possible. And yet here we find ourselves 10 years later on, bringing that capability to the market. And Oceaneering is one of the pioneers there. What do you think has been the biggest leap in that 10 years to enable that? Has it been technological or has it been cultural?
It's a bit of both. I find there's two different camps out there. There are those people who are quite comfortable having a Tesla car pull into a garage or pick you up at a valet and drive on, and there's those people that absolutely will not touch it. So as technology changes, you've got to jump on and embrace it. We have seen computer algorithms and software develop so fast in the past 5 years. I mean, look at iPhones. 10 years ago, we didn't have an iPhone. Today, they can do things that supercomputers 15 years ago couldn't do. So technology is changing by the minute, and we're just finding and embracing new ways to incorporate that technology in everything. So a lot of the things that even I spoke about today, I said we're still in development. We're never going to be out of development. Everything we do is a learned process, and we just keep adding and adding to that. As new things come along, we'll put that in, we'll change this. Can this make it better? All for that reliability, that safety factor, and getting those folks comfortable. So, where are we going to be at with autonomous cars, driving around on the roads? This is the way things are going. I think we're going to see more in 5 years' time than we do currently right now. So, the batteries in these cars, they're constantly changing. So before you could only get, 50, 60, 70, 100 kilometers out of a battery before it was completely flat. Now we're talking about getting hundreds of kilometers and beyond that. So things are really changing. And I look at that industry, I look at the auto industry and compare it to our industry. As we learn things there, it's very similar technology, it's very similar algorithms. And as I mentioned, Oceaneering also builds these land vehicles that we use in factories to take parts from one place to like a bin to an assembly line, for instance. And in that is all land-based sensory technology. It is the same platform, but we're learning how that incorporates into those industries and moving that directly into the subsea worlds. So I love it. I think the correlation between both is pretty cool.
Cool.
Yep.
So Keith, no surprise that I'm going to be coming to you next with a question, kind of around the houses here. I might change the order next time around, so be warned. For you, it's a slightly different paradigm, I guess, because you're transitioning from what you called was an R&D hub to now being a service provider. What's the biggest challenge there for you?
I think so. Originally, when we started out, we were actually focused on a survey delivery, a commercial survey business. The timing we thought was great with low oil prices. We thought everyone would be biting their hand off for new sort of this new generation of AUV technology, which could potentially have significant cost savings and take the hassle out of some of these operations. It was actually met with skepticism. No one was really in our circles willing to give it a go. To a certain degree, I mean, no one wants to put their hand up on new tech. It's let's get down to business and get through this period of time. That's where the R&D element of the business came to bear. So that's where we started looking at, well, what other things are out there. The proof of concept model was a big part of our business for a while. The beauty is that we have conventional meteorological oceanographic systems we can put in the water. So where a client doesn't particularly want or has skepticism around AUV or similar tech, we could challenge it. We could say, okay, well we can deploy traditional systems, and we can put the AUV in. Let's see how we go. And that was, for us, was a really good way to sort of build confidence with our clients, expand out our services. So a lot of proof of concept, a lot of trialing and testing. Also knowing the market. We're not here to take over the world. We're very specific about the tools, the specific tools for specific applications. So when we talked about in my presentation, shallow water pipeline inspection, that was our focus. The technology that we bring to that is not the technology we have on the shelves. We're not trying to do a round hole with a square peg. Other applications, the Ivor 3 is not appropriate. And even some applications, autonomy is not appropriate. So it's really finding the right solution to fit with our clients. So proof of concept, know your market, build that confidence, and then develop from there. And like Chris has alluded to, things are going to change and have been changing so fast that you have to be agile. You have to be willing to adopt new practice, new sensor technology, et cetera, et cetera. So you can never be stationary in this market.
Indeed, and I think that's a salient point, that things are changing. So last summer, I was lucky enough to be invited to be a judge at the Office of Naval Research RoboSub competition held at SPAWAR in San Diego, which was really cool. So there were teams from 53 different entries from around the world, from places like Japan and Egypt and Korea and China to the USA, of course, Brazil, Canada, Norway. And they ranged from middle school children up to postgrad, real range of capabilities. But the one constant element of it was that they all had, within their systems, they all had what 5 years ago would have been considered cutting edge, or 5 or 10 years ago. So computer vision algorithms to identify an object and then home in on it. That's now middle school subjects, it appears. So as we advance into AI, into machine learning capabilities for potentially for data processing in mission and potentially for control, what do you see as the easiest win, perhaps the easiest thing to implement, perhaps, but also perhaps what do you see as the stumbling blocks, the roadblocks? What might be put in our way to getting that working? Now, Trevor, you mentioned some automated processing. So is AI a part of that, or is it just automating manual processes as they stand today? How much do your customers trust automated process?
Well, the bulk of our work is in construction support, and we find that is too reactive and dynamic. Where you're doing first pass, second pass trenching with intermediate surveys. So it's not the production line of thousands of kilometers of multi-beam survey. So whilst we automate our processes hugely to sort of meet the ever demanding faster turnaround times, we don't see much opportunity for the artificial intelligence to process our data. So we just focus on automation rather than AI.
So that's an interesting concept and quite different, Chris, from what you were talking about using AI on the vehicle. Now, is that purely for data interpretation or is it for vehicle control? And how do you train it? Because of course AI takes a long time to actually become efficient.
Yes, I mean this is why we've spent thousands of hours in this living lab in Norway is training the artificial intelligence platform, machine learning. We started with a computer that is running this type of technology, and then we built an ROV or AUV system around that by aiding it with different sensors. So we started with the machine learning. And then we've scaled up from there. We've run very similar platforms to Freedom with the government before. We've designed things, but it's all running that same type of artificial intelligence. It is something that we're feeding. We're constantly developing it. We have teams working on this, but to us, that is the platform. That is the brains of this entire organization, because it moves to all our different other manufacturing facilities into all the different products that we do, just not subsea. So our artificial intelligence, absolutely, machine learning, and it's a constant education. I mean, it's teaching us, we're learning from it, and we're providing it with information. So it's a back and forth.
Cool. Now, Keith, with your survey provider head on and I guess your marine science head on, what would you like to see from advanced data processing, AI, machine learning? What would you love manufacturers like Kongsberg or like Bluefin to bring to you and say, we can do this, it's cool?
I think there's certainly some intelligence that can be brought to the vehicles in terms of well, I say a specific application. So let's say oil spill response or plume monitoring. So having the intelligence for the platform to identify, the plume edge, so delineating where the plume edge on a threshold would be, for example. So building that capability, I mean, it's there, but it just really needs to be applied and developed. I mean, from our point of view is accessibility to data. So automation of data processing is something we're looking at, not specifically around pipeline inspection, but looking at water quality programs. The idea being you're ultimately report ready, automated reporting when you come off the boat. So that's something we're developing. Yeah, certainly looking at inside the Vertec group, the Geo Oceans with their fleet of 20 ROVs, have got a Go Vision computer aided looking at imagery for benthic habitats, for example, and even moving that now to sort of pipeline and asset monitoring, bridging across to that. I think as technology develops, the diversity of technology kind of funnels down as technology goes forward. The systems become more similar. You start taking the best bits of everything and you sort of bring these systems together. The next step really is in that software. That to us is the drag foot, if you like. So we're certainly looking at that into 2021, 2022 in terms of how we can speed up those processes.
Cool. So Adam, final question for you then. As a manufacturer, I'm not trying to put you on the spot here, because I don't want to know what Bluefin are developing. I want to know what you as an individual, what one magic thing, if we as an industry could develop it, what do you think would be super cool? What would be a game changer? Sure.
I mean, to speak to what Keith mentioned earlier, as UUVs, USVs, and really all domains have evolved, a combined operation focused on, sending out a robot to go perform a subsea mission, transfer that data to a USV, and then up to a satellite link and back to a home base station so that somebody can review that data immediately is really the ultimate goal. That changes, we've seen a shift from really that proof of concept model to an operational focus for subsea equipment, specifically UUVs and USVs. And so, in the future, I think any way we can decrease the time or the overall operation efficiency of these robotics and combine those multi-domains, that's really the ultimate goal for us.
Excellent. Thank you very much. So with that, I would love to be able to give you a nice loud round of applause, but unfortunately, in these virtual times, I have to struggle and give you a virtual round of applause. Thank you very much, everybody, for participating and for speaking. That draws to a close this session. I'd like to encourage those people who've watched and participated to go and join in the virtual exhibition hall and the other conference sessions that are going to be on as part of the Oceanology International Connect event. And I wish you all a wonderful day. Thank you very much.
Thanks, Richard.